Here's an information slide. So let me begin. So first of all, welcome everybody to today's SoFiE Seminar. I'm Andrew Patton, the organizer of the series. Today, I'm very happy to be hosting Christian Gourieroux as our speaker. And his discussant is Anders Rahbek from the University of Copenhagen. We'll use the usual format as in past weeks. We'll have 40 minutes for the speaker, 10 minutes or so for the discussant, and then 5 or 10 minutes for Q&A at the end. If the questions run over, we'll all move to a Hangout session. We'll turn off the recordings and then we can all talk a little bit more. In the middle of the presentation, if you have questions, you can use the raise your hand feature, or you can use the Q&A box at the bottom of your Zoom screen. Okay, and with that, I'll hand it all over to Christian. Christian, the screen is yours.
So you see my slides?
Yes.
Yes, okay. So I can start?
Please, go ahead.
Okay, so this is a joint paper with Joanne. I will try to explain what is our idea in a rather simple way, I think. So this is just the problem of taking into account the long-run component when we are doing the predictions. So this is a problem which is rather well known in the literature, starting, for instance, with Friedman, with permanent consumption, for instance. But this is especially important in the recent literature that you can see in Bontali-Aron, for instance, with this idea of shocks, and the fact that you can have shocks on a transitory component or shock on a permanent component. If you have some shocks on the transitory component or the short-term component, if you want, we expect a short-run effect, but no long-run effect, but the reverse when you shock the permanent component. So the difficulty is, of course, to define what is a permanent component. And one specificity, in fact, of our paper is to consider, in fact, this question in a strictly stationary framework. So the idea is not to say that the long-run component is non-stationary, a trend, if you want, but it is a part of stationary observations. And so the question is, so there are two different questions. So the first one is, of course, how to identify the long-run component in practice and how to measure its impacts. Likely, it will be rather complicated, of course, to detect it, since in general, it is hidden by the short-run component, in particular, if you are considering a given set of observations. And but we have an idea of that it can exist, and an idea of identification which underlies, in fact, the paper by Fama-French in '88. Since what we have seen is by considering a series of stock returns, usually when we regress YT on YT minus 1, for instance, at the daily level, this is not significant. So this is just a linear regression, of course. And so we have what is called an efficient market. But if instead of that, we first smooth the data, so we consider a kind of average return or return, if you want, on a period of length h, and then we regress on YT minus HH, it becomes significant. So this is rather strange when we have this kind of result in mind, since from the interpretation point of view, this is what is called the long-run predictability puzzle. So you can say that the market are efficient in the short run, but not efficient in the long run, which is very strange, and this is not compatible with theoretical definition of what is an efficient market, which is a condition of martingale or something like that. And more strange, the profit cannot be shown in the short term, but you are sure in the long term, which is the consequence of this kind of result. And so, so from an interpretation point of view, this is very puzzling. And likely this puzzle is due to a spurious correlation somewhere. So when computing, in fact, the usual SCF, maybe we are seeing low correlation, low serial correlation, but in fact, we have to be very careful with this kind of observation, since maybe what we are seeing from the usual application, in fact, of time series literature and the ACF maybe has no real physical significance. Maybe we have missed something, okay? And so the aim of this paper is a very simple example, rather simple, in which, in fact, we consider a model in which the observed series is the sum of two components, independent components. The first one with a short-run interpretation and typically a pure strong white noise, so very erratic if you want, and the second one, a long-run component. And of course, the new thing in the paper is the specification of this component. Okay. So what we have introduced in the paper is a kind of stationary long-run component, and this is simply a kind of autoregressive process. So you can see this autoregressive process, which is autoregressive process of order 1. The errors are IID. They are centered and unitary variance. But you can see there is something which is rather special in this specification. You have a correlation coefficient rho, and the variance is square root 1 minus rho square. So what is arising is that if rho is very close to 1, so if rho is smaller than 1 but tends to 1, when the number of observations tends to infinity, you can see that, of course, you have at the limit a unit root. But not only a unit root, you have also a variance which is equal to 0. And so this is a kind of limit of stationary process. Okay, so it is stationary, so even if you have a unit root, but since you have at the same time, in fact, the small sigma, we are considering the behavior in a neighborhood of another kind of process. This other kind of process, you can see if rho is equal to 1, you have just YLT equal YLT minus 1. And so this is what is called irregular process when you consider, for instance, the wall decomposition. This is the process which is constant in time, but with a stochastic level. And so, of course, when rho tends to 1, you are very close to something which is constant in time, but with a stochastic level, okay? And so this is very different from the standard local unity framework. And so the idea is to introduce this kind of specification for the long-run component and to consider what are the consequences for identification, for estimation purpose, and so on. So what are the dynamic properties? So more precisely here, you can see the model is a bit different in the sense that now I have introduced some weights, okay, some weights for the short-run component and for the long-run component, okay? And so I can now manage the two weights, okay, in order to have different mixtures of short-run and long-run. So, these weights are chosen in order to have YT with a unit variance. So you have for the basic component XLT and XST unit variance. And so with a right choice of a weight, as you can see with a square root, you have automatically unit variance for YT. And so PS, for instance, is a fraction of the total variance due to the short-run component. So what is the interpretation of rho tending to 1? In fact, when you have this kind of autoregressive process of order 1 with Gaussian noise, I will consider Gaussian noise here to understand what is arising. We know that this autoregressive process of order 1 is in fact time discretized Ornstein-Uhlenbeck process. So maybe we can introduce an underlying Ornstein-Uhlenbeck process, and you have here the dynamic corresponding to this diffusion equation dxt equal minus kxt dt plus eta twt. And so, in fact, the idea is to say that the XLT is the observation of this underlying process at a time which is, I will say, small t over capital T. And in this case, you will have this kind of limiting behavior. So the XT, which is here, is absolutely not observed. This is a kind of underlying process in a ultra-long time unit. Okay, this is an ultra-long time unit. So this is something which is as if you consider daily observation, it is not observed, but daily observation on XLT, in fact, you have considered that these are high frequency data coming from an underlying with a very, very large time unit, something like a century or a millennium, something like that, okay? And so the daily things can be interpreted as high frequency data of something else, okay? And so, but of course, contrary to the usual high frequency data, the day is fixed, and this is this unit of the underlying process that is going to infinity with capital T, okay? And so in this case, what is arising is simply the fact that depending of this choice, in fact, we have a kind of time deformation. We are changing time, and by changing time, of course, we change the correlation, and of course, you can reach this correlation very close to 1. Just to have an idea of limiting case, if you have an infinite compression of time, you have a white noise. If you have an infinite dilatation of time, you have an irregular process, this process whose trajectories are constant in time by stochastic, okay? So to understand what is done, of course, you have just to consider trajectories. So this is the trajectories of a AR1 process. And we are changing, in fact, the time simply, okay? And so we are starting from a small row, for instance. So this is almost white noise. And after, but in fact, what we are doing is just changing, in some sense, the time unit, okay? And by changing the time unit, you can see that you have more and more smooth things. And at the limit, for instance, you can see that we have the impression that, or sometimes it is at the beginning, for instance, here, almost constant, not exactly. After we have the impression that maybe some trends, and after another kind of small trend and so on. But this kind of limit is stationary. Okay, the trajectories are stationary, even if you have the impression that you have some local trend somewhere. So this is simply a consequence of this time deformation, okay? And so this is basically the idea. And of course, what we are interested in is when we have a mixture of this kind of long-run component with noise. And here, this is, for instance, a kind of mixture. The first one with equal weights, for instance, and we are seeing this effect of a long-run component. But if you have a large noise, you can see that this is much more difficult to detect, okay? And so this is the idea. The idea is, of course, so this is the goal of this paper, which is to try to detect, in fact, this underlying long-run component when you have observation, for instance, corresponding to the figures at the bottom, okay? Just to have a comparison, so just to have a comparison with literature, for instance, another literature, since you have a part of a literature that tries to decompose, in fact, a given series into different frequencies. This is usually done by an analysis in frequency domain or by wavelets or this kind of thing. If we consider what is arising, for instance, when you consider a kind of analysis in frequency domain, what is known is that it corresponds to a kind of decomposition of the trajectories into combination of cosine and sine. Okay, and you have a frequency W, and you have a coefficient capital A, capital B that depend on W, and they have some weak properties concerning their first and second order moments. Okay, in particular, they are not correlated. The problem with this kind of decomposition is that even if the A and B are not correlated, they are strongly dependent. In general, they are mutually dependent. And so it is very difficult to shock separately, in fact, these different components, okay, due to this dependence between the components, okay? And this is very different to what is proposed in the paper, since the alternative here written, for instance, for G equal to, as in the previous slide, we can superpose, in fact, different autoregressive process independent with different time deformation and try to consider the decomposition. And since the epsilon gt in this decomposition are independent, we can check them separately. And so, and take, of course, see what are the consequences of a shock, short-run shock, long-run shock, and so on at the different time unit, which are the different terms, if you want, in some sense. Okay. So there is a first result in the paper, which is for identification. Okay, so so in fact, we have different things to identify, which are, of course, the importance of a correlation, or the importance of time deformation, if you want, and the weights of the different components, but also possibly the distribution of a shock, the distribution of the epsilon. And so the first result is saying that we can identify all the things whenever, in fact, the rho J are distant. Okay, and in fact, the first parameters, the weights and the time deformation, if you want, of the rho J, are identifiable from the two autocovariances of YT only. And after, once you have estimated this kind of thing, you can identify all the distributions of the underlying shocks. So this is just to understand how it works. So here, for instance, this is for J equal 2. So this is the identification of weights and the rho. And so we have just to compute the covariance, the autocovariance, and you can see the form of the autocovariance. And so typically, for instance, to have a consistent estimator, not efficient, of course, but consistent, you have just to use this covariance in an appropriate way. So you can see, for instance, for the rho, which is here, this is not rho 1. This is not the ratio of gamma 1 by gamma 0, but this is the ratio of gamma 2 by gamma 1. So this is as if we are using an instrument somewhere. And for the weights, you have gamma 1 square over gamma 2. And so you have here a simple way to have consistent estimators under closed form. Okay. For the identification of the distribution of the errors, it can be done by pairwise analysis of a second characteristic function. So second characteristic function, this is the logarithm of expectation of exponential transform of, and you have here a combination of YT and YT minus 1. So we just consider what is arising at lag 1, but in a nonlinear way. Okay, in a linear way, it is in the gamma, but you see here, this is nonlinear. And so it is possible to identify, in fact, the distribution of epsilon, the distribution of the YL, and automatically of epsilon L after. And we have also a closed form expression of this second log characteristic function, the second characteristic function of epsilon S YL as function of psi. Okay, so intuitively, the psi will be estimated by its empirical counterpart. And after, you can deduce under closed form the derivative of B, the derivative of C. And since we know that for U equals 0, this is equal, for instance, the expectation of the exponential is equal to 1, we integrate and we have a result. And so it will be the basis of the estimation approaches. So we'll see later on the estimation approaches. What are the dynamic properties of this model? So there is something which is important to see is to understand what has been seen in the literature before, in particular in Banzali-Aron. So in Banzali-Aron, what is done is to consider this type of model, for instance. So here, this is the long run component. You have XLT here, X1T if you want, plus a noise. Okay, and after we can perform the theoretical regressions. For instance, theoretical regression, we are considering the sum, for instance, here, and we can consider what is the estimation of beta, or first, what is the theoretical value of this regression coefficient and how it depends on H. We can also consider the theoretical correlation of the square of a correlation between the dependent and explanatory variables in these regression models. So it is possible to derive the explicit form, okay, at least in the Gaussian case. And we will see that automatically we have an shaped pattern when we plot the theoretical result as a function of h, okay? So here, this is an idea of a theoretical one as function of h. And of course, it depends on the value of rho, which are close to 1. And of course, the variance, which has to be rather close to 0 sometimes. So, so this is the shape, okay? So this is for the theoretical result. And so maybe we have to go more in detail, since we don't know what is arising when h tends to infinity first, and we don't know what are the consequences of a usual estimation of rho, okay, and of what is an estimation of rho taking into account the model. And so there is something which concerns the behavior when h tends to infinity, okay, here. And of course, we have a limit, okay? So this is when h tends to infinity, you can see that rho is tending to 1 at the speed 1 over h, okay? And so we have a limit. And so this kind of pattern with a bomb tends to a limit, and the limit depends on delta, which is the speed of convergence to 1, okay? And so you can see that this is from the model. And so in the model, you have two parts, okay? You have the short-run part and the long-run part, long-run component, and you can see that it doesn't depend on the weights. It only depends, of course, on the long-run component itself, okay? So no effect on the P and on the part coming from the short-run component for this limit. So this is what I have announced first. So now we can compare theoretical regression and the usual estimation. So this is a simulated path, okay? So you can see a simulated path. So you can see, this is for YT, of course. So you can see the high variability. So this is due to the noise. And you have the underlying long-run component somewhere. And so we arrive to this kind of graph, okay? So the line, the curve above correspond to the usual estimation. So we are just computing by regression, okay? The empirical regression, the YT on the average. Okay, so this is what is done usually, for instance, in Banzaliaron. And so you see, we are seeing at the beginning for small h, nothing, okay? Almost efficient market in the usual interpretation, and after it tends to 1, okay? But if you take into account now what is the true one is the second curve when you go down, and you see the bump that is announced, and you have a kind of convergence when h tends to infinity. And now you can also consider what is arising when in this formula for the true one, using the model, you replace by estimator of rho and the estimator of sigma and this kind of thing. And you see something else, okay? We see the bump, but we see that we have a very strong bias, okay? So it is not enough to know what are the theoretical properties, we are also to understand why some estimation methods, even if you know what is the form of this regression coefficient in terms of a rho and sigma square for given h, what are the consequences of the estimation and why you have this kind of bias arising. So statistical inference, you have, of course, two different parts for statistical inference, or 3 different parts we will see. First, we have to understand what are the properties of this model. Okay, when we consider some usual statistics, standard one, for instance, you average on the data on the Y, or you compute some usual ACF, for instance, and after to understand what are the properties, theoretical one now, for asymptotic inference, and maybe if we have time, some part concerning the test and the Bayesian analysis. So clearly, of course, this is in some sense, this is very similar to what has been obtained in the standard local to unity approach, but local to unity approach close to non-stationarity. Here, this is close to this irregular stationary component. Okay, and so first we will see what is arising if we apply the usual ACF that are in the softwares. Okay, and with a standard confidence band. So likely we have already seen that it was rather strange, okay, in particular for the estimation. So likely you have something very special. So we don't have to be very surprised. So these are the usual ACF, okay, and we have depending on the number of observations. And of course, you have here, this is equiweighted, and equiweighted, in general, you see nothing. You see nothing except if you have a very, very, very large number of observations. If you have a very, very large number of observations, we observe what is sometimes observed on the series, which is now some significant estimated correlations, I will say, but at a level which is almost constant and far below the value 1. Okay. But of course, this is when it is equiweighted. If, of course, you have more weights on the noise, more weights of the noise, we continue to see almost nothing. Okay, so it means that this, this is very misleading, this ACF, since the ACF is not enough in some sense to detect this long-run component if you have large noise. So it is clear intuitively that it will not be easy to detect, but this is not the right tool to do that. I will escape this one. So we have also to be very careful about the standard interpretation that we have, okay? For instance, we can compute what is the true value of gamma 1. We have seen before. The true value of gamma 1, this is not rho, okay? This is rho multiplied by the weight of a long-run component. And so this is why we have this kind of instrumental estimation of a rho. Since if you are just taking gamma 1 divided gamma 0, which is the rho 1 is here, in fact, when rho is close to 1, you are not estimating the rho, you are estimating the weight of a long-run component, okay? And so this is something else, okay? And so we don't have to interpret in the usual way. Also, we see something strange in the bounds, in the confidence bound in the ACF, even if they are not computed in the right way or estimated in the right way, which is in fact the interpretation of the hypothesis. In general, when we consider this ACF, we want to test the hypothesis of white noise against the hypothesis that it is not white noise. So we privilegiate the hypothesis of white noise. But this is not what we have to do here, since in general, we are interested in detecting the long-run component, and so we don't have to privilegiate the null hypothesis of white noise. We have to privilegiate the null hypothesis of there exists a long-run component. So we have to be very careful in the standard interpretations. The estimation, we have seen the identification, and so we can estimate following, in fact, what has been done for the identification. For instance, the estimates of rho and the weight from the sample autocovariance that provide consistent estimator, the estimates of the distribution of errors from pairwise, empirical pairwise characteristic functions. So you have some estimation on the slides and on the paper, but I will escape this part, okay? So you can just, to have an idea, you can see this is for, so these are the two distributions of the two noises. And in fact, you can see the real part and imaginary part. And so it has to be interpreted. This is the real part of the second characteristic function, the imaginary part of the second characteristic function. If you have, for instance, a Gaussian distribution, of course, you will have a very special form, okay? And you can see here, for instance, some parabolic form and something like that, okay? But I will not discuss this point, which is the non-parametric estimation of distribution. So now what is the right asymptotic inference in this case? So first, we have to derive a kind of law of large number, okay? And the law of large numbers, so we consider simply the average. So what is arising when we average, taking into account the presence of this long-run stationary component? In fact, it will depend on the speed of convergence of rho to 1, okay, as a function of a number of observations. So sometimes you can see a first case, okay, when h times 1 minus rho tends to 0, okay, the condition mean has a limit, and you can see that the limit is proportional to YLT, okay, so it is stochastic, okay, so the limit is stochastic. We are not very surprised since we have some convergence toward this irregular process, which has a stochastic level. So this is what is arising. And the conditional variance goes to 0. So we have really a convergence, okay? Now you have a limiting case in which, in fact, h times 1 minus rho tends to a constant gamma. And you can see also the limit is stochastic. And so the limit is stochastic and depends of the value YLT. And sometimes, of course, it tends to infinity. It tends to 0 systematically. When it tends to 0 systematically, this is the usual law of large number, since in my model, in fact, the expectation is equal to 0. So the standard law of large number is case free. But what we are interested in, of course, is the intermediate case, where, in fact, we have something different from what is usual in the literature, okay? So we have to go a bit further. By considering the sample autocorrelation now. Since you have seen, of course, knowing simply what is the asymptotic behavior of the average is not very useful for us, since in general, we base, in fact, our estimation, in particular at the beginning, from the autocorrelation. And here, these are the sample autocorrelation to have an idea of what is arising. So this is what I have said before. So this is our model. The rho is tending to 1, simply since we are assuming that it is coming from a kind of Ornstein-Uhlenbeck process coming from a very, very large time unit, okay? So so the virtual time unit going to infinity, going from the year to century to millennium, and so on and so on. And so not very surprising, it corresponds, the technique is very similar to what has been developed for high frequency data. And we have a convergence, for instance, in distribution to, and here you have a ratio of stochastic integrals, okay? And you can see the stochastic integrals written on this underlying process. So, and the dynamic of this underlying process depends on K, you can see, and you have, so the effect of K parameters, but also the effect of the weights. And of course, this limit, you can see now the limit is stochastic. The limit is stochastic, and of course, this is the problem, okay? So we are not sure that it converges to something constant, but it converges to something which is random, since the X tilde is random itself. And so, of course, we will have a modification of the confidence bounds, okay? But we can have a confidence bounds by considering of something, by considering, of course, the quantiles associated to this ratio of stochastic integrals. So they can be used to compute theoretically, when H is large, the confidence intervals. Here, these are confidence intervals, these are the finite sample properties. So we can consider this is for different value of T, or the number of observations. Maybe we can consider larger value, for instance, for 500. So you can see, this is not very surprising. This is not very surprising. So you can see you have a table here with different value of the weights and different value of rho. And of course, what is arising intuitively is that when rho is very, very, very close to 1, as it is done here, this is very, very close to the trajectories for a constant. And so the constant is difficult to identify compared, for instance, to an intercept parameter that you have introduced. Okay, and so likely we have some kind of identification problem somewhere, so kind of weak identification, and the identification is weaker and weaker when rho tends to 1. Okay, but you can see. Okay, so of course this is not necessarily very precise. Okay, as you can see. Except that you can see that the true value is within the interval, but the interval is rather asymmetric, so you have some skewness. It is not surprising that this is not very accurate, since we want to detect a very, very small signal in a very large noise. Okay, so this is what we expect, but this is much better than saying that this underlying long-run component does not exist at all. Since if you are saying that it does not exist at all, you will not take it into account when you evaluate the long-run risk. And we want to take into account when we evaluate the long-run risk, even if we know that it will not be very accurate and that we will have a large uncertainty on this kind of thing, except to the certainty that is usually assumed when you don't take it into account. But something which is more interesting is that, of course, here this is to have an idea of this value of rho, but maybe you have more accurate results if you are interested in some other statistic you are interested in. For instance, you can take you can try to see what is the probability of detecting the long-run component now. And you can see that, oh, maybe we are almost able sometimes to detect it. So this is in percent, of course. And you can see that for t equal 500, we try to detect. For t equal 1000, you do continue to detect. And so, in fact, we can see that we can have an idea of the presence of such components. So what is difficult is to know the level and what is the risk associated to this component, but not the detection. Okay. So just maybe to, I am close to conclude, if I understand clearly. So you have here a part of the paper, which is the equivalent in a Bayesian framework. So this is related with a paper of Schafeider-Songaron in Econometrica. In fact, they are using somewhere a model which is very close. This is the second row that you have here. This is rho xt minus 1 plus sigma square root 1 minus rho square epsilon t. And it is clear that this model can be rewritten as a usual autoregressive model with coefficient r and eta, for instance. And what is arising is that, in fact, we have a change of parameter. And the change of parameter can create an identification problem. So when you consider, for instance, the usual parametric efficiency bounds for the standard autoregressive model, you can see there is no problem at all. This is a diagonal matrix and this kind of thing. But when we consider the parametric efficiency bound for the other one, you have to take into account the Jacobian. And you can see the Jacobian is not invertible when rho is equal to 1. Okay. And so we have an identification problem. And so the question is, oh, when, for instance, we introduce a prior, uniform prior, do you have to introduce the uniform prior on parameter R eta, or do you have to introduce a uniform prior on parameter rho and sigma? Likely rho and sigma, since these are this one that have interpretation, in particular the rho in terms of time deformation and time unit. So this is the structural interpretation. But also, not only this kind of thing, what has been seen is that intuitively with this parameter of interest concerning time deformation, we have an identification problem. And what we have to do likely is not only to introduce a prior on these parameters instead of a usual one, but we have to allow the priors to change with capital T with a number of observations in order to introduce the equivalent of local alternative in a Bayesian framework and to focus on what is arising close to the lack of identification. Just to conclude. So you see just a modeling of a ultra long run component by a time deformation, depending on the number of observations. So, and this possibility to use the usual high frequency data technique, but in another way, okay, simply with this interpretation of daily values, consider high frequency values corresponding to an underlying process written in an ultra large time unit. We are to have a local expansion around something else, which is the irregular stationary process, even if you have unit roots. So you have process with unit root but are stationary, which is the message also. And you have new statistical inference, of course. And what has been seen by this extension of a law of large number is that this long-term risk, you can see, continue to depend on the long-run component. So it cannot be diversified, which is the main message. Not only it cannot be diversified, but we have some difficulty to evaluate the risk, which is seen by the estimates, which are not very accurate, but this is what we were expected for that. So you have here some references, and that's all. I am in time.
Perfect. Thank you very much, Christian.
Almost.
Just done. Okay, that was great. I'm teaching PhD time series right now. This is great stuff. I've got kind of exam questions, ideas from watching your talk just now. So now I'm going to call on.
Except if the students are attending the seminar.
Yes, well, if they're attending, then good for them. They get a head start on the exam. Yes. Okay. Well, let me turn it over to Anders. So, Christian, if you wouldn't mind, there we go. Great.
It's okay.
Thank you.
So I just share the screen, or?
Yes, please go ahead.
Okay, right. All right. I just begin, or?
Yes, please go ahead.
Okay. All right. Yeah. So thank you for inviting me as a discussant. It's always an honor and a pleasure to read any paper from Christian and his co-author. And this one is not an exception. It's an amazing paper. In fact, the more times you read it, I can highly recommend to read it, the more times you realize so many new things and reinvestigate and rethink about your time series analysis and analysis in general. So just to sort of be very, very short on what's going on, I mean, one of the strangest thing in time series, for me at least, still is the fact that the most constant dynamic process is xt equal xt minus 1. And then it's the most non-stationary in a way. If you just add a noise, then it becomes the famous random walk, which is sort of generating a lot of issues that on the one hand is very, very stable, in another way is from a statistical point of view, or at least asymptotic point of view, non-stationary. In terms of statistical modeling, we usually embed it in an autoregressive model and proceed by doing QMLE or something. And in the Gourieroux and Yashak paper, the AR process is combined, which you could call a measurement error or the long and the short run, or that many different framing of putting it. So I have an observation equation where xt is the autoregression and the eta is an uncorrelated or independent noise. And estimation proceed by, for example, Kalman filter techniques, or as advocated in the paper, non-parametric Walker-based semi-parametric combinations, which seem to perform all right despite the quite large sort of confidence bands. But what I will do, if I could make it, yeah, I will mainly focus, or I will only focus on the long run component. So just to rewrite and restate what has already been stated many times, it's an autoregressive process where the variance is of a parametric form which decreases as rho tends to 1 by the square root of 1 minus rho squared. And it's also mentioned by Christian as when rho is close to 1, one may consider close to 1 asymptotics or near integrated asymptotics or whatever we call it, where we localize the parameter to be 1 plus, say, pi over n, and consider the asymptotics of such a process to study sort of the limiting behavior. This was the slide on the Ornstein-Uhlenbeck type process in the presentation. And if we rewrite the long run process in terms of the pi, we can rewrite it in terms of the difference of xt, it becomes rho minus 1. And then we have still the square root of 1 minus rho squared in front of the epsilon, which then rho minus 1 becomes the pi over n. So you have the local parameter there, and you have the local parameter also entering in the variance in the form discussed. So this would be sort of the localization or the drifting sequence that I'm discussing a little bit. And just something that I was sort of curious about was this 1 minus rho squared. What happens there? Doesn't it become 1 over n squared? But the fact is that because of the cross products, you maintain that the order of the scaling is 1 over n, which is, I found, also in line with a paper by Moon et al., which is cited in the paper, where they use, instead of square root of 1 minus rho squared, they use square root of 1 minus rho. But that was just the sort of the order of convergence. What happens is, as was also mentioned by Christian, is that in the limit, as n tends to infinity, we get an Ornstein-Uhlenbeck process, which looks exactly like a standard Ornstein-Uhlenbeck process, except that we have this little term out here, which you could, of course, put up in front. It's just a scalar, and you could also call it 2 pi. But there's a reason why I do it, because on the next slides, I want to try to sort of generalize this long run component to a multivariate component to see how things will work, given that I'm also quite interested in this from a multivariate perspective. And just to be assured that things make sense, when pi is 0, indeed the 2 pi becomes 0, and the process j, if you want, is 0, and you get this phenomenon that when rho is essentially 1, or pi is essentially 0, or pi over n is 0, we get exactly that. You get this, the most, say, constant system in the world. Xt is xt minus 1, or a 0 for the j process. As a p-dimensional try, I considered the following. So everything is as before, except now I replace rho by the identity matrix plus a pi matrix, which is p by p. I move the 1 to the left, so we have a delta xt, and here is rho minus 1, which we call pi. And then you have the covariance here. Like this, and the square root of I minus, then you need the rho squared, and the rho squared is I plus pi times I plus pi transposed in the multivariate case. So this would be a possible multivariate extension. And just as sort of a check, if we put pi to 0, which is everything becomes a unit root, or rho equal to 1 for all components if you want, then indeed xt becomes the constant process with a x0 as the initial point. And as for Gourieroux and Yashak's paper, if rho is smaller than 1, or here, if all the spectral radius or the maximum eigenvalues of 1 plus pi is smaller than 1, then xt is a p-dimensional stationary process. So how can we sort of, I've tried to play around with sort of trying to embed the various aspects by looking at the structure on the pi matrix. And as you know, I've done a lot of co-integration analysis, and it's tempting to look at the reduced rank of pi. Now, if pi has reduced rank, say R less than P, we factorize this as the product between two matrices, alpha and beta, each of rank R. The process will look as in the square here. And this looks fairly much as a sort of standard co-integrated bar model, except for the variance component. And indeed, the common trends or the random walks here becomes just constants, whereas the stationary directions, they are still stationary. So now we have sort of embedded some of the ideas, but in a way we want pi to be full rank and approach zero at some rate. So what if I instead make pi tend to zero at the rate of n as a matrix? Then the process will look like this. And instead of writing the I plus pi prime, I just note this fact that I discussed before, that the covariance with this way is of order 1 over n. And we get p minus q, or p minus the rank being constants, and the remaining linear combinations being sort of these local long run components, where we have the important covariance component out here. And in the limit, we get, again, this Ornstein-Uhlenbeck type process, where the difference is this component, which is sort of not in the, say, usual ways of writing the Ornstein-Uhlenbeck. Of course, you could have it, but here it's sort of, I emphasize it, that this is the sort of the pi plus for the univariate case, or the 2 pi. And again, we have that the component has variance 0 for certain cases, namely the case where these two, with the inner product between the eta and the delta, if the rank is 1, or just in general, the eta prime times delta is a 0 matrix. Of course, you could also try to combine it. So you have some true unit roots, some co-integrated unit roots, and some local to unity, and in which case the model becomes more or less even more unreadable. But here it is. So we have pi as the sum of the two here, and then we have I minus I plus pi squared, if you want, and the square root of that as the variance component. And again, writing the process again here, just to make sure we remember it. Then in this sort of mixed framework where we have some, say, classic plus some non-classic components, I believe it's possible to have to make the following theorem or proposition, that in this system up here, the stationary combinations, we have R of those. They are up to the order of 1 over the square root of n, behaving exactly like standard, if you believe standard co-integration is standard co-integrated processes. And then you have the remaining components behaving exactly like we want them, namely such that they are normalized, tend weakly to Ornstein-Uhlenbeck type process, which will say with a variance which is 0 under the constraint that either you can be sort of rough and say there's no other components, but you can also be a little bit more, I don't know, innocent or less strict by restricting and sort of looking into linear combinations. But the essence is that, so I said, yes, I can try to generalize, and I hope that I try to sort of generalize in a way that, I don't know, may or may not be useful for further discussions. But so this will mark the end of my discussion. Again, thank you very much for letting me discuss this paper.
All right, thanks very much, Anders. Very interesting extensions. That's great. Well, maybe given the time, I think what we could do is have Christian, if you'd like to respond. I don't know how you respond to that discussion, but I'll let you figure that out. And then we'll move, we'll take questions and answers in the Hangout session after the formal seminar. So maybe Anders, well, I'm not sure. Christian, do you want to look at Anders' slides or should we stop sharing?
I think Christian should unmute.
Oh, yes, yes.
Okay, you hear me now?
Yes.
Yes.
Okay, so thanks Anders for this development. In fact, we are trying to extend, of course, but we are not following this route. In fact, what we have in mind are two different things. First, you have seen that we have this high frequency data interpretation, and so in fact, we can apply to all the class of the file models. For instance, for the autoregressive gamma models or for jumps and this kind of thing. So this is what we have in mind. For instance, rare disaster, to take them into account, even if you have not observed disaster in the past, or if autoregressive gamma, for instance, to have this, so this is multivariate. So this kind of time deformation on the mean and this kind of time deformation and the volatility together, and to see what are the consequences of this kind of thing. So this is this kind of nonlinear dynamic extension that we have in mind with maybe multidimensionality, for instance, if you have mean and variance. This is the idea that we have. What we are doing also is to consider what are the consequences for pricing of this kind of figure to price. This long-run company that are here. But I think no, this is interesting what you are proposing. So I would say that the difficulty that we have is maybe linked to another problem that I don't know how to solve in general, which is the problem of how to aggregate time deformation. Since intuitively what is said is that you have different components with different time deformation, something like that. And if you have, for instance, the idea of market time, for instance, you have a kind of market time for Europe, a market time for US, and you have a market time for the exchange rate. And we don't know how to combine. Okay? But really they are linked. They are automatically linked and in a nonlinear way. So this is this kind of thing. This is why we try to treat together, for instance, volatility, co-volatility matrices and this kind of thing with the extension.
Okay. Well, let's pause it there. So, Anders, if you wouldn't mind stopping the sharing.
I'd be very happy to stop.
Thank you very much. All right. So before we move to the Hangout session, let me do a quick advertisement for the next SoFiE seminar. The next SoFiE seminar will be in 2 weeks' time. On May 3, our speaker will be Serena Ng from Columbia University, and her discussant will be Marcus Pelger from Stanford. So please join us then in 2 weeks' time.